Hello everyone, today we'll talk about the problem minimum number of moves to seat everyone. Along a line, we're given n seats at certain positions and n students at certain positions. We want for every student to be seated at a seat, and only one student can occupy a single seat, so they will have to move to reach a seat and sit there. And we cannot move the seats, we can move the students. In one step we can move one student 1 unit to the left or to the right. And you want to return the minimum number of moves that are required to seat every student. So, if we knew what student reaches what seat, so for instance we have a seat here, seat here, seat here, and let's say a student would be a T, so 2 students here and maybe 1 student here. If we knew which student reaches which seat, then the result is just the sum of absolute values of differences between the position of a student and their seat. So the problem is reduced now to just deciding which student reaches which seat. And you might be able to guess that the best solution is to sort the seats and students in the same order and then match them appropriately. So the leftmost seat goes to the leftmost student, the next seat to the next student, and so on. In that case, if you're satisfied that you agree that this greedy solution will work, to implement it you just have to sort both of the arrays, sum up those absolute values of differences and return them. So that is already a solution. And I guess the last part is to actually convince yourself that this solution works, or to actually prove that this solution works. Now, proving that this algorithm works will be left as an exercise to the watcher, but to not leave you empty-handed, if you're unfamiliar with something called exchange argument, so this is an argument for the correctness of a solution based on exchanging some things in solutions, then I'd like to introduce you to it because it may be helpful in proving that this is indeed an optimal solution. So an exchange argument goes something like this. And the standard idea is that you have your solution, so this is the solution that is returned by our algorithm, and then this is the second solution, so this is optimal. And now, if our solution is, well, it cannot be better than optimal because optimal by definition is the best. It can be equal and then there is no problem because our solution is still optimal. Or it can be worse than the optimal solution. Then we have a problem. And now, if the scores of our solution and the optimal solution are different, then of course they have to differ at some decision they make. And maybe you can show that you can select one of those decisions that they make differently, change the decision in the optimal algorithm to be the same as we would make in our algorithm. So that would typically be the first decision that the optimal algorithm does differently than we do. And then if you can show that the score of the optimal algorithm does not decrease, right? So that change does not give us a worse score, then you can keep doing that until there are no longer any differences between the two solutions. And thus you have shown that you can improve, or at least not destroy, the optimal solution and reach the solution that is given by our algorithm. And if you first assume that our algorithm gave a worse solution, then this is a contradiction. So we have proven that, of course, our solution is better. And probably in this case what you want to look is perhaps just to look at the leftmost seat. If that leftmost seat is assigned to the leftmost student, then everything is okay. So you have to assume that the leftmost seat is, and of course, if the leftmost seat is assigned to the leftmost student, you can forget about that seat and forget about that student and look at the leftmost remaining seat and student. And either all of those will be assigned as in our solution, so there is no difference between those two solutions, ours is optimal, or you can reach the first point where there is a difference. And now you just have to analyze what happens if you change the decision that was made, so the leftmost seat was assigned not to the leftmost student. So how about assigning it to the leftmost student, and assigning the student that was assigned in this optimal solution to the leftmost seat? Let's assign them the seat that the leftmost student was assigned in the optimal solution, and try to analyze how the score changes. So this is a typical argument, but this is an exercise for you.